Hello everyone, my name is Tomek Lisp, and in this series of short videos, I will introduce you to programming web applications in Clojure. Even though Clojure is mostly used inside of the Java virtual machine, we will not be using Java web application mechanisms directly, as many concepts differ from classical servlets, filters, and so on. It is possible to write Clojure web apps with servlets, but it is very cumbersome and inelegant and hence not the preferred way to go. However, because this is Clojure, once you get to know the basic concepts and approaches, web development becomes much more easier and elegant than before. In the first section, we'll learn how to configure Clojure project, connect necessary tools, and write our first HTTP request handlers. Please note that there are a number of Clojure web application frameworks and utilities, but in these videos, we will focus on the general techniques, not the specific frameworks or implementations. Still, there are two tools that are the basics of virtually every modern Clojure web application: Line-ingen, the build tool, and Ring, which maps HTTP and other requests into Clojure function calls, somewhat similar to Rack in Ruby and WSGI in Python. Line-ingen, or simply Line, is a de facto Clojure industry standard for managing automation in projects. To install Line 2, just follow the instructions from the website lineingen.org. The usual procedure is to download the Line script, place it on your path, and mark it as executable. For Windows users, there is also an installer. Having the Line script in place, we can create a new Clojure project by typing line new and the project name, in this case project 1. This command has created the project CLG file and the basic directory structure for the project, along with an example namespace and test code. Ring, on the other hand, provides elegant abstraction over handling HTTP and other requests by mapping them to Clojure function calls. We can define our project dependencies in the project CLG file, and we'll start with Ring. The Ring 1.2.0 library bundles the following libraries: Ring Core, the basic library; Ring Devel, the development functionalities; Ring Servlet, the adapter for running Ring web apps inside of Java servlet containers; and Ring Jetty adapter, the adapter to be used when we want to run the Ring web app as a standalone Jetty instance. Now, we have our project initialized and we have connected the Ring library. In the next video, we will configure the Ring plugin to simplify most of our development. In this video, we will see how to configure and use the Line Ring plugin to simplify tasks that are common to web application development in Clojure. There are a number of tasks common to the Ring web application development process: pointing Ring, our handler function; calling specific functions upon web application creation or destruction, for example, database connection pool initialization or destruction; starting a standalone web server instance for development. This is usually done through the use of the Jetty adapter, which is provided by the Ring library; bundling our web application into a package, either a plain old WAR file that we can deploy in our favorite web application container, or a standalone uber.jar file that, once viewed by java-jar, will start the appropriate Jetty instance. And finally, aiding our web development cycle with dynamic code reloading when changes in source files are detected. Lucky for us, another thing that we can use with Line-ingen are plugins, which simplify some common tasks in our project. For the issues mentioned a moment ago, the best solution available is the Line Ring plugin. The project defined in a previous video, we can connect Line Ring to it by editing project CLG file. The plugins keyword contains a collection of plugin references, and we will define it as containing Line Ring plugin in version 0.8.7. We also need to specify at least a reference to our Ring handler. Don't worry about it not existing yet. We will create it in the next video. Please note, as opposed to servlet web apps, you can have only one handler per project. We will dig into how to use that characteristic to our advantage in the forthcoming videos. We can also, but don't have to, specify functions to be invoked upon container initialization and destruction. will work for both standalone Jetty adapter Ring web applications as well for the ones packaged into a WAR file. This concludes basic Ring configuration. For more options, it is good to visit the plugins page on GitHub. In the next video, we will define our first web application functions. In this video, we will see how to write a simple Ring handler that will respond to HTTP requests. We will also build basic functions that will be called upon initialization and destruction of our web application. The Ring handler function that we define is our gateway to reacting to HTTP requests, accessing their data, request headers for example, and returning an appropriate response. With initialization destruction functions, we can manage common resources, such as the configuration or database connection pool. We will dive deeper into this matter in the appropriate videos later on. The actual Ring handler is simply a standard Clojure function that takes a request map as an argument and returns a response map as the result. We will ignore the request parameter for now and simply return the static content hello Clojure for every request that comes to us. This will be regardless of the type of request or the path request. Of course, we can specify many more keywords in the response map. If we don't, the servlet container will add default value, such as HTTP status code equal to 200. We can also define an initialization function, which does not do much right now. It only displays a diagnostic message to the standard output. Please note that since we reference functions by name, we can name it or any other the way we want. On init is just an example name configured in project CLG. The counterpart for the initialization handler is a function invoked upon the closing of our web application. Please remember that such a function might not be invoked if our container is destroyed abruptly, for example by a power loss or JVM crash. Our onDestroy handler also only displays diagnostic messages to the standard output. This concludes the writing of the basic Ring initialization, request and destruction handlers. We have implemented the first Ring-related code, and it turns out that there is no magic there or special boilerplate code, just standard Clojure function. In the next video, we'll finally run our web application and connect to it with a web browser. In this video, we'll see how we can use the Line and Line Ring plugins to start a development web server running our Ring handlers. We'll also see how we can change our code while running the web server and see to it that it gets reloaded automatically. The Line Ring plugin will allow us to run our code inside of a simple web application container, which is actually a Jetty used as a library. We have previously referenced and implemented example handler and initialization destruction functions. Now, it's time to see them in action. The simplest way to start a Ring server with the Jetty adapter is to run line ring server headless. We can also run the line ring server, but that would start a browser, which is not necessary at this moment. Please note that upon starting our server, a diagnostic message from the onInit function has been shown. When we decided to shut down the server with Ctrl+C, the diagnostic message from the onDestroy function has been displayed. Please note that on Mac OS X, the diagnostic message will not be displayed as Command-C kills the JVM completely. As you can see, the Ring plugin looks for the first available port, starting with 3000. We can easily override the setting by providing the environment variable port or SSL port for HTTPS, or by configuring the project CLG file, or by supplying the preferred port number as a command line argument to line. With our development server running, we can connect to it using the Firefox web browser, for example. Please observe that our handler captures all requests, and since it serves the same response, we get the same result in a browser for different paths. The common task when it comes to development is applying your changes to the project and running the code. With Java, in the simplest scenario, we would have to redeploy the WAR file or use some kind of live code reloading tool. For example, the one bundled with the Java debugger. With Clojure, we can just leverage the existing mechanisms provided by the language. What's even better, that the line ring plugin does that automatically for us. Observe what happens if we alter the example handler definition in the core CLG file, with the web application server still running in another terminal. The source files are being monitored for changes and reloaded when they are updated. Of course, such features come at a performance cost and are enabled only on the development server, and even then, they can be disabled with configuration options or environment settings. We have started our web app server with defined handler. Using mechanisms provided by the line ring plugin, we have also applied the changes in our code to a live running instance. In the next video, we will learn how to package our web application into a nifty WAR or standalone Uberjar package. In this video, we will see how we can use the line ring and line ring plugins to package our web application using two different techniques, by building a standalone Uberjar file or a standard WAR web application file. Once we have developed a certain set of features in our application, we need to distribute it to different environments. Usually, it is not feasible performance-wise to use development methods to run the code in a production or test environment. Therefore, we need to package our software in a convenient way for further distribution, versioning, ease of deployment, and so on. Either as a standalone Uberjar file that contains all the dependencies, or as a WAR file that is ready to be deployed in our favorite web application container, for example Apache Tomcat or even IBM WebSphere. Uberjar is a Java archive file that contains our project and all the necessary libraries needed to run, including even the Clojure runtime. One thing that line ring plugin does for us when building Uberjar is that it adds the necessary ring libraries with their dependency trees and sets the main class in the meta manifest mf description. Once this is done, we can start our web application inside of embedded Jetty container just by typing java-jar and the path to the Uberjar file. Such an approach works well when our web application is simple and does not require any advanced functionalities provided by the web application container. Another approach to distributing our web application written in Clojure is to leverage the existing web application containers, because of the features granted by them, to run multiple web apps on a single port and save resources, or simply due to company or customer policy. We are using Uberwar instead of the WAR command to include all the necessary libraries in our WAR file. We can also provide a name for the WAR file that is going to be built, which can be used, for example, by Tomcat to determine the request path. We can use any specification-compliant web application container. In our case, we will use the newest Tomcat version. Let's start the Tomcat instance with the bin startup shell script and look at the log file with the tail command. We will copy the WAR file into Tomcat's web apps directory to trigger deployment. Now that the web application has been deployed, we can see the result in a web browser, for example Firefox. Please observe that since we've deployed our web application as a WAR file, it is available under the /project1 context only. As we can see, there are a number of ways to run and distribute Clojure web applications. From the simple development server run from line, through the whole app and Jetty bundled together in an executable jar file, and up to leveraging the existing Java web application containers with the WAR file. That concludes the first series of videos regarding web application and development in Clojure. In the next section, we will learn more about ring handlers and responses. In this section, we will learn in depth about handler concepts in Ring. First, we will need to understand what a handler is. Just as we have servlets in standard Java web applications, Ring's approach to responding to HTTP requests is built around handlers. We've seen handlers at work in the previous videos. It was just a function that took an input map and returned a result map. We will now learn that although simple, handlers are a powerful and versatile tool when it comes to web application development. As we can see, a handler just takes a request map and as an input and returns a response map as an output. The Ring handler can only access information from the request map and can only return the response map. It does not mean that we cannot access thread-bound variables or external resources, such as databases or web services from handlers. But, for example, we can easily test our handlers by providing the appropriate request maps and expecting a certain output, just as with any other Clojure function. Please observe that we are not even referring any Ring namespaces in our namespace. For the handler function, at this moment, Ring is just convention for request and response, nothing more. Let's see if we can invoke the function from REPL. We can start REPL by simply typing line REPL in the terminal. The process that starts will have access to the project libraries and source codes. With the REPL started, we can reference our project namespace and invoke the example handler. Since our handler does not use the request map at the moment, we can pass it an empty map. The result is as expected, just a map with an entry for the body keyword containing the response string. Since the handler is a function and takes a map as an input parameter, we can make also use of Clojure's destructuring syntax. Let's assume that we only need the URI attribute from the request map, that is the request path. We can clearly put that in the handler definition as we would do with any other function. We can still retain access to the request object this way by using the S keyword in the destructuring syntax. Now we have a basic understanding of how handlers work in Clojure. There's no magic behind them really. As we treat it as any other function, we can invoke it from REPL, write unit tests for it, use Clojure destructuring syntax, and so on. In the next video, we will focus on the input information that is provided by Ring. In this video, we will learn in depth what the request map contains when handling standard Ring HTTP requests. We can safely assume that almost every web application needs to access some input parameters from the HTTP requester. Even when serving static HTML files, there's at least a need to determine which file have to be sent. Ring provides us with all the available information using the request map provided as an input for our handler function. Let's change our handler to return the request that is receiving so we can review what's given to us by default. Having updated our handler, we will start the Ring development server and connect to it using the Firefox web browser. We use the URI test path for the request, but our handler still catches all HTTP requests directed to the TCP port that development server listens on. We can now review the request object. First, we have the basic HTTP information: path, host, remote address, the method, query string, and so on. We will also get a map of request headers and the body as a stream. HTTP input from Jetty extends the standard servlet input stream, which extends the basic Java I/O input stream. As you might have probably noticed, Some features that are usually available when programming with Java servlets are missing. For example, we don't have a parameters map and there is no trace of cookies or sessions. The reason is that they can be coerced or calculated using the provided information. Such functionality is usually implemented by middleware, which we will describe once we are done with handlers. We have learned that Ring handlers expect a map as an input and that Ring provides basic request information in that map. Now, as we understand what's available to us in the input parameters of the Ring handler, we can proceed to the next video, where we'll learn what the response values expected by Ring are. In this video, we will learn how to provide meaningful return values from Ring handler. Once our handler has completed performing its logic, we need to return an appropriate response to the browser. Ring expects us to return a map as the result of our handler function. With this map, we can control what will be returned to the browser. Please note that in actual application, you will rarely access or create such map directly. It is most likely that you will have an abstraction layer built over it or just use functions provided by Ring. Still, it is necessary to understand what's going on underneath to make proper use of them. First of all, there is the body keyword. We've seen it in action before. It controls the content of the HTTP response. We do not have to put a string in it. We can also use a stream or a Java IO file reference. For example, let's create a simple text file and return its content. Now, we can see the file contents in the browser. The other important thing is a status code, which is mapped directly into the HTTP response status code. Let's change our handler to return the 500 internal server error. This time, we will use CURL to see the whole HTTP communication and not only the result. The response body stays the same, but the error code is now 500 instead of 200. We are using the Ring development server here, so the source file gets reloaded automatically without server restart. The last thing that can be returned to Ring are headers. They are provided as a map of header names as keys and header values as values. We can also use headers to set the cookies, content type, and so on. Everything that's supported by the browsers or other HTTP client. Let's return a 301 status and a location header from our handler to redirect the browser to the Ring homepage on GitHub. Also, let's set a cookie named test to the value 1. There is no special abstraction for cookies in our code yet, but it is very easy to implement. Obviously, it is provided by Ring by default. Now we know exactly how to control the HTTP response returned by Ring after invoking our handler. In the next video, we'll learn how to introduce routing mechanisms in our web app, dispatching HTTP requests to different handlers. In this video, I will present how we can utilize things learned in previous videos to dispatch calls to different handlers. As I have shown before, a Ring instance will direct all the requests to a single handler. Of course, we don't want to have all our logic inside just one function. Luckily for us, as handlers are just functions, we can easily implement an over-handler, which will direct invocations to different handlers based on its configuration and request data. Please note that there are already popular frameworks in Clojure doing exactly that. We will get back to them at the appropriate time. Right now, it is more important to understand how routing can work, not learn some specific framework. Our simplified routing handler will select a handler to invoke through a simple conp statement, with the request URI as a tested value. We can, of course, utilize any information provided in a request or session or even external data sources to decide on routing. The handler available under /test1 path will return the string test1 as the response. The second handler, invoked when somebody accesses the /test2 path, will redirect the HTTP client to the Ring Clojure page on GitHub. Let's start the development server now and see how our simple routing behaved. Everything is as expected. The test1 handler displays test1 text, while test2 handler has redirected us to GitHub. This is a significant upgrade. If we want to start serving data under the /test3 path, all we have to do is to change the root configuration in the handler and add the appropriate function. The development server still runs in the same process, and we don't have to restart it or change the project configuration or any descriptors. We can even have the handler in a different namespace. Let's implement it, and then let's reference it in our root handler. Please observe that the Ring development server has loaded the new namespace and refreshed our handlers. We have seen here that handlers can be composed just as easily as any function. In the next video, we will compose the handlers not only for routing, but also for more advanced features. In this video, I will show more advanced techniques that are made available by Ring handlers. Routing based on URLs is one thing, but every web application requires support for more common mechanisms. In this video, I will show how to implement the correct 404 handler and how to handle exceptions using Ring handler functions. Let's see what happens if we decide to enter an address that is not mapped to any handler function. We have received the standard 404 not found page in response. Let's see if we can return a custom HTTP 404 not found error code in such cases. Because Ring uses standard processing conventions, we can compose our routing with different functions. So, let's add another routing layer that will dispatch requests to the route handler, but if we get a new response, it will return the appropriate 404 HTTP error code. This way, we can have a routing hierarchy instead of one big function. Now, we have to switch the handler used by Ring and restart the development server, as we are changing the very project definition and not only the handler function. Please observe that we haven't changed the existing handler. We've just added another layer of abstraction on the request processing. The existing handlers don't know anything about the new handler. We just compose them to work together. Another common case is handling exception. Let's reuse the existing wrapping handler and introduce exception into one of our handlers. We will simply return 500 internal server error and the error stack trace as a body. Now we can observe the stack trace in the browser. Please note that in the actual application, middleware already exists for that. We are using error handling only for purposes of illustration. That concludes the second section of the video series. We have learned that handlers are just functions, and that it's possible to combine them and use them to our advantage. It has also been shown that Ring request and response objects are plain Clojure maps that we can manipulate just like any other. In the next section, we'll dive deep into how middleware works and how it can be used to simplify our web application architecture. In this section, we will learn in depth about the middleware concept in Ring. First of all, let's see what middleware is. Then, we'll create our own middleware. Finally, we'll review the useful middleware available with Ring. As we have seen in the previous section, Ring handlers are just ordinary Clojure functions. And as in every computer program, we were able to distinguish some tasks common to all use cases. For example, exception handling. What we did then was to compose our handlers explicitly. This clearly has a significant drawback, because the handlers need to know about other handlers to perform those tasks. Luckily for us, there is a better way. In Clojure, we can treat functions as any other values. So, instead of directly referencing other handler functions, we can pass them as arguments. Let's create a simple function doing that. Such functions are called middleware in Ring. Our middleware will log the path of the request. This illustrates how middleware works. It is a function that takes another function as an argument. We assume that the function is a handler. Then, middleware wraps the given function in a new function, which is in fact a request handler, as it takes a request as an input and returns a response map. This new request handler invokes the original request handler function after logging the request URI. Since our middleware returns the function, we use def and not defn to declare the new handler from it. The created middleware does not know anything about the wrapping handler. It is only in the full handler definition that we are combining the two together. It is very useful because we can define our middleware as a totally different software package without any reference to our actual handlers. Please note that this is only for demonstration purposes. Real-world logging should use a logging framework such as Clojure Tools Logging instead of Printl in the first place. Before we use our new middleware in the Ring server, let's demonstrate that it is still just a function and it does not require Ring to be invoked. Let's start an REPL with a line REPL and load our namespace. If we invoke our middleware function, we will get another function as a result. Let's invoke the generated function and see what happens. As expected, we have received a response map from our function and observed two messages printed to the standard output. Let's switch the handler referenced by Ring to a new one, which is using middleware. And then let's see the new middleware in action by starting the Ring development server. As you can see, the 404 not found handler still works properly, and we have received a diagnostic message from our middleware as well. We have explained a new concept in web application programming in Clojure, middleware. Middleware allows us to separate common tasks and mechanisms into functions independent from the rest of the project and the actual handler. In the next video, we will transform mechanisms created in section 2 into middleware. In this video, we will transform two mechanisms introduced in the previous section as handler, 404 not found and exception handling, into a middleware. In the previous video, we have introduced a sample middleware function, which added some basic logging mechanism to the request handling pipeline. But we also have two mechanisms from one of the previous sections, which will be of benefit because it is more portable and reusable, being rewritten as middleware. That is, 404 not found error support and exception handling. Let's start with the 404 not found mechanism. Our middleware will call the original handler to receive the response back. If there is no actual response, it will return a default 404 not found message. Then, let's attach this middleware to our full handler function and see it in action by starting the Ring development server with line. As you can see, the new middleware has detected that the page has not been found and has returned an appropriate error message. Now we can rewrite our second common mechanism to a middleware form. Please note that this time we will use two functions, one with actual implementation of the middleware and the other just wrapping everything up. This technique is useful when we're developing more complex middleware and we want to reload it without refreshing other components. For example, restarting the Ring server or rebuilding the entire handler var. It also makes the code for the middleware cleaner. We can now reorganize our full handler with a threading macro for increased readability. The threading macro takes a value and then invokes the first form with that value as a first argument. It then takes the result and invokes the next form, and so on. Therefore, it is ideal if we want to arrange our middleware in a chain of execution. Please note that because our middleware will wrap one another, the order of the actual invocation when processing HTTP requests will be reversed in regard to the order of middleware provided to the threading macro. Let's see if the exception handling middleware works properly. As expected, we have received the error message. The main difference between the current situation and what we had in the previous section is that the middleware is totally independent of each other and can be mixed to our liking in a clear and concise way. We have reworked our mechanisms implemented as handlers to be middleware. Now, the dependency between each component is clearly defined, and the not found error and exception handling is independent of any other code in our project. In the next video, we will showcase how the middleware can alter request and response maps. In this video, we will learn how middleware can be used to alter request and response maps. As we have seen in previous videos, Ring requests and responses are simple Clojure maps with some designated keys. We have also introduced the middleware concept, where we were controlling the flow of handler invocation from different sources. One thing that is also very useful is the fact that with middleware, we are able to intercept and alter the request and response. We can use middleware, for example, to parse query strings and provide query parameters as a map, or we can use middleware to support cookie parsing and creation. Such middleware, as you have probably guessed, is already provided by Ring, along with a bunch of useful functions. But for showcasing purposes, let's implement simple middleware that will make the URI lowercase, making our routing case insensitive and make the response capitalized. Just as before, we have an actual middleware logic implementation in the case middleware function and a wrapper within the wrap case middleware function. Our middleware first updates the request map using the updateIn function. Then, we invoke the handler with a new request map and collect the response. If the body of a response is a string, we update it with a Clojure string capitalized function, otherwise we just return it as it might be a stream or a file reference. Now we can attach the middleware. Since we are already using the threading macro, we can just add another reference to the chain. We'll add the wrap case middleware at the beginning, so it won't affect the 404 error message, which will allow us to illustrate that the order of middleware is important. Let's start our Ring development server and try out the new middleware. As expected, the 404 not found mid handler is not affected and returns a message for the original URI. Test 4 is in capital letters, for example. To fix that problem, we can rearrange the order of middleware. Having done that, we see that the not found error messages now display the URI in mid lowercase. We have implemented a simple middleware that has altered the request and response maps. The other middleware and request handlers stay as they were, as they are independent of each other. We have also seen that the order in which we use middleware is important. In the next video, we will connect the file serving middleware provided by Ring. In this video, we'll connect some common Ring middleware to our project. In previous videos, we have created some middleware that aided us in common tasks. Needless to say, we are not the first web application programmers in Clojure, and such middleware has been created before. Fortunately, most of such middleware is neatly packaged into Ring. In this video, we will connect example Ring middleware to our project. Let's start with the static resource serving middleware. In one of our handlers, we are returning a file reference. But what if we had a bunch of resources, such as JavaScript, style sheets, and images? Of course, in production environment, we should not use Clojure to serve static files. It is better to serve them from a standard HTTP server, or even better, from a content delivery network. But still, for purposes of development, it is convenient to serve them along with dynamic content directly from the Clojure development server. To connect the middleware, all we have to do is reference it in our namespace, so Clojure would load a file and connect it to our main handler, just like our custom handlers or middleware functions. We can either use middleware from the Ring middleware file namespace to serve static files from a directory on the local file system, or we can use middleware from the Ring middleware resource namespace to serve files from our project's class path. We will use the latter as it is more convenient at this moment. We will get the resource middleware to work before the not found middleware kicks in, otherwise it would not be possible to return a static file. We should also use the file info middleware to provide the appropriate content type and HTTP headers that were modified last. The file info middleware will also work if we decide to return the Java IO file handler from a function other than the resource middleware. Please note that we have provided additional parameters to wrap resource, and that's possible because of how threading macro works. If you are unfamiliar with threading macros, it will be a good idea to look up some more examples. It is a really useful tool for data transformations in Clojure. All we need to do is create the appropriate directories. A default directory to store static resources in our project is named resources. It has already been created by line new, so let's just create a subdirectory named public. With the public directory in place, we can put static resources there, for example, a simple JavaScript and stylesheet files. Let's start the Ring development server and see the resources. We have connected the provided Ring resource middleware to our project to serve the static file. It has added more functionality to our web application without any changes in other components, except of course the main handler. Please note that Ring contains much more useful middleware packages. We will be using them in future videos, but you can also review a complete list on the Ring website. That concludes middleware basics for now. In the next sections, we will cover more practical topics, forms and session handling. In this section, we will use the knowledge gathered in previous sections to learn some practical techniques used when developing Clojure web applications. First of all, we will familiarize ourselves with accessing form data. After that, we'll focus on generating HTML from handler. Then, we will learn how to manipulate cookies in the Ring web application. And finally, we will see how to access session data. If you are developing a Clojure web application, there is a good chance you will want to accept input from users in some way. Otherwise, plain old HTML files would suffice. Such data can be provided in a number of ways, but the simplest is to utilize two mechanisms used by web browsers: query strings and form submission with POST or GET. Both of them provide a common key equals value format. Naturally, we would not like to write yet another parser for them. So, let's just use middleware provided by Ring. There are two functions that we want to use, and please note that the order of usage is very important here, as one of them depends on the other. First, we will connect Ring middleware params. This middleware parses request parameters both from the query string and the post data, if available. The result is stored in three request map entries, which are query params for query string params, form params for post data params, and finally params being merged with the two above. One inconvenient thing here is that map keys are just strings, not Clojure keywords. Luckily for us, there is another middleware, Ring middleware keyword params, that does exactly what we need and keywordizes parameter names. After connecting the middleware, we need to create a handler that will utilize the new keywords in the request map and attach it to root handler. With the handler and middleware in place, we can create a simple HTML form, for example, a login form. We will use middleware from the previous section to serve the static files. The form will have the post method, as we can test the get parameters by simply using our browser. Let's observe our handler in action. First, the query parameter. Then we can see the post method in action. In both cases, Ring middleware has successfully mapped the request parameters for easy access. There is one input type that requires special treatment when it comes to form handling in web application. That is, file upload or, speaking more generally, multi-part forms. Clojure and Ring are not different in this regard, and as you have probably guessed, yes, there is middleware to aid us in this matter. The middleware is provided in the Ring middleware multiple params namespace, and we have connected it to our namespace, and now we can connect it to our handler. The default store for multiple parameters saves the file to a temporary directory. Files get deleted from it after at least an hour. Let's enhance our form handler to display the temporary file location on the server's file system. Other attributes of the uploaded file will be visible through parameter maps, where they are represented as a regular Clojure map. The temp file entry in the upload map contains a reference to a standard Java I/O file object, so we can reference it like any other file. Let's test our enhanced form in the Firefox web browser. As you can see, we have received a lot of useful information regarding the uploaded file. The attributes are, of course, dependent on the implementation of use store, and those displayed come from the default implementation. Please note that we now have our parameters in multi-part param and not in form params. We have connected the appropriate middleware to access the request parameters, that is, the query string and form data, in a convenient way. We have also introduced a way to handle uploads. In the next video, we will learn how to generate HTML content from the Clojure web application handler. In this video, we will learn how to generate HTML content with Clojure. HTML is the standard language that is used to control what the web browser displays to the user. Our HTML will not always be static, as it was in the previous examples, and we would surely need a way to generate it in a convenient way. Please note that in real-world project, it is recommended to apply one of the existing libraries for generating HTML, for example, Hiccup or Clojure or Enlive. But to learn how basic things work, we will use only the standard mechanism provided by Clojure. Generally speaking, Lisp and HTML or any other markup language are similar. You just wrap expressions into one another. Let's create a simple mechanism that will translate between nested vectors and HTML code. It takes a value on input, and if it is a vector, it renders its first element as an HTML tag and calls itself on the rest. If the value is anything else, it just converts it to string using the str function. This mechanism is also extremely simple and does not support HTML attributes for tags and also does not escape HTML content. Now, let's use our simple HTML generating mechanism to render some HTML pages. We will enhance the form handler used in previous video, that is, the one used to output text plain content, and change it to HTML. Since we might want to use the same template for different pages, we can extract a layout function. Then, let's rebuild the form handler to return proper HTML content. Please note that we have changed the content type header to text HTML. We are using the layout function defined moments ago, and we have put our parameters in the pre tag to preserve formatting. Once we have our handler generating HTML, let's see it in action. The HTML output looks way better than plain text. But please remember that this approach just showcases how to generate HTML in a simplified way. If we were to enter some special HTML character, like greater than, it would be rendered as any other. We have successfully introduced a new mechanism for generating HTML content from Clojure handlers, which allowed us to demonstrate the basic approach that we can apply. Please remember that the real-world applications will require us to take much more into consideration while generating HTML, and it is better to use an existing library. As we focus on general mechanisms, not some specific implementations now, the example was as simple as possible. However, we will cover one of the libraries, Hiccup, in upcoming section. In the next video, we will learn how to use cookie manipulation mechanisms in Ring. In this video, we will learn how to manipulate cookies in Clojure web applications. Cookies are tiny bits of information the web application can store in a user's browser. They are useful when we want to persist states or some preferences, and they can also be used to store the session identifier, or, in some implementations, even a whole session. We have seen in the previous videos that we can access request and set response headers, allowing us to effectively manage cookies. Fortunately, middleware already exists to simplify that, allowing us to treat cookies as standard Clojure maps. The middleware is provided in the Ring middleware cookies namespace. Let's add it to our namespace. Then we can alter our form handling handler to store the supplied username in a cookie. As you can see, we don't use any magic variables. We just add the cookie's key to our response map to contain the desired cookie. We'll use a session cookie, which expires after the user closes the browser, but it is also possible to supply other cookie options, path, expiry date, and so on. We'll create another handler to display cookies. This handler will render HTML as well, so we can reuse our layout function and HTML generation mechanism from the previous video. We will also need to update the routing handler. Let's start our Ring development server now and see the cookie handling middleware in action. We can see that the cookie has been set in Firebug, and it contains the username that we've provided as input. Of course, this is a cookie that is under browser's control, so we can alter it to our liking if we want to. We have applied a cookie management middleware provided by Ring to our application. This middleware enhances the Ring request and response to allow us to access and change cookies. In the next video, we will learn how to access and manipulate session data. In this video, we will learn how to access and manipulate sessions in Ring web application. In the previous video, we have stored the provided username without verifying the password in a cookie for further reference. That approach had one significant drawback. That is, the cookie was stored in a user's browser, and the user was able to manipulate its value. We can of course try signing or encrypting the cookie, but the simplest way to overcome this limitation is to use session mechanism provided by Ring. Like almost every common mechanism provided by Ring, session handling is made available by middleware. This middleware is located in the Ring middleware session namespace. Let's connect it to our web application. You can also control for how long the session cookie should be stored in the browser. Should it be sent via HTTPS only? To which path should the session cookie apply? And so on. If we don't specify the max age of the cookie, it will exist as long as the browser session is open. The last option is useful if we want to have two different kinds of session available under different paths on the same host application. The default implementation for the session store is to use JVM's memory. If we won't supply any other option, this store will be used. Ring also provides an implementation where we store the session in an encrypted cookie client side, but we can implement or use other session storages, for example to store sessions in MongoDB or SQL database. For the sake of simplicity, we will use the default in-memory storage. This memory binds a session to a specific JVM instance, so it might be not sufficient for more complex scenarios, like having multiple JVM instances and a load balancer. Each session is referenced by a unique identifier stored in a cookie that is named Ring Session by default. With the middleware in place, we can now add session attributes to form handler. Let's store a username from the params form and increase an invocation counter. We'll also add another handler to display what is stored in the session. Please note that if our application will store other information in the session as well, we should merge the session map from the request with our new values, therefore preserving other session entries. Now, let's start the Ring development server and observe session handling in action. As you can see, the session provides state management that is controlled at the server side. There is a functionality that we might find is lacking in sessions. Sometimes we would like to destroy the user's session entirely, for example, to provide the logout functionality. To destroy a session in Ring, all we have to do is to set it to nil in the response map. Let's add a logout handler that will do exactly that and return a plain text message. We will also need to add the new handler to the root handler. We have connected and applied session middleware to our handler. Please note that this middleware is highly configurable, and we can even provide implementations that are different from the ones that come along with Ring. This concludes this section of videos. We have learned many practical techniques here: how to access form and query parameters, how to handle file upload, how to generate HTML from Clojure, how to handle cookies, and finally, how to manipulate sessions. In the next section, we'll learn how to create RESTful APIs with Ring. In this section, we'll learn how to build RESTful web APIs in Clojure. In previous sections, we have covered the basic tools needed to build a standard HTML-based application. But HTTP is used not only for serving HTML or static contents, it can also be used to build modern APIs. In such a scenario, instead of generating HTML responses passed by a browser and presented to a user, we simply expose our application's business logic as dedicated operation. This can be used for integration with other applications, possibly created in different technologies, or to simply create a JavaScript application that will invoke REST API to communicate with the backend. The concept of communicating between machines is as old as the first computer networks themselves, and fortunately, it has evolved a lot. So, at this moment, the most popular approach seems to be the RESTful one. Fortunately, Clojure provides us with means to build such APIs very quickly and, most importantly, integrated with existing data structure mechanisms. The RESTful approach is built around the concept of resources, and it utilizes the means provided by HTTP, namely paths and verbs like post, get, put, or delete. We model our APIs after the resources that they provide, and we usually map basic operations to HTTP verbs. For example, to retrieve a resource data, we use the get verb. To alter it, we use put or patch verbs. In the RESTful approach, there is also the convention of implementing identifiers as a part of request URI. The most common format for transmitting information is JavaScript object notation, JSON. If we restrict ourselves to the Clojure world, we might also consider the EDN format for ClojureScript to consume. But let's focus on JSON for now. Let's start by building means for routing that are REST compliant and therefore take not only the path into account, but also match the HTTP verb and extract named arguments from the path. Please note that framework already exists for Clojure Ring supporting that, Compojure for example. Still, to fully understand how things work, we'll provide an example implementation that is trivial and non-optimal but simple. To keep things separated, we will create another namespace to contain our routing code. Now we can implement a function that verifies if the Ring request matches a desired verb and path pattern. If the request matches a desired verb and path pattern, the function tries to extract argument names and values from it. I have used simple printl statements to showcase matching steps. Of course, in real applications, it would be mandatory to use the appropriate logging framework. The matching part is somewhat complex. First, we replace all path spec fragments separated by slashes that start with a colon with the appropriate regular expression group. Then, if the request URI matches the regular expressions we have created, we extract the names of the path spec fragments replaced before and finally merge them with actual value. This approach is of course very simple and has some drawbacks, like having regular expressions in our path spec would mess up the mechanism, but it will do for illustrative purposes. We will also apply the keyword function to argument names for easier manipulation, just as we will do with query and form parameters. As you can see, the root arguments are now associated with the request map, and a new map is returned. Having the function to determine if the request applies to root, we can implement more flexible routing than before. First, we have the routing function, which invokes all supplied root functions in order until one of them returns something other than nil or false. After that, we will have a helper function that wraps the supplied function in the root matches invocation. It is somewhat similar to middleware, as it alters the request map to contain our routing mechanism ready. We can now rewrite our root handler to utilize the actual routing mechanism. In addition to reflecting existing roots with the new mechanism, I have added an invocation for the test1 handler with the ID argument. I have also implemented two roots using the form handler, one for the get invocation and the other for the post method. I have also added the root parameters display to the test1 handler to illustrate that the mechanism worked as we intended it to. Let's fire up the Ring development server and see our routing mechanism in action. Test1 handler gets invoked with and without an ID, responding accordingly. If we add some more paths to the path, the result will be 404 not found. Let's see if the forms are still working. As you can see, the new routing handler does not interfere with the middleware connected to our project. They are still independent of each other. We can also see what happens if we try to use an unmapped HTTP verb, for example, issuing the delete command to /test/156. As you can see, the delete verb has no mapping yet, and therefore we have received a 404 not found response. In the actual REST interface, we might prefer 405 not implemented, but let's keep things simple for now. This concludes the first part of the Building RESTful APIs section. We have implemented a simplistic routing mechanism that allowed us to provide RESTful route alongside regular ones. In the next video, we will define REST mappings for a resource that will accept and return JSON data. In this video, we will implement an example RESTful API that manages a simple resource. Let's say we want to implement an API for managing a blog. The blog entries are a resource that we want to manage. We need to create, update, list, and sometimes even remove them. Having all the routing mechanisms, we can easily implement correct mapping of HTTP requests to handlers. Something else that we need is JSON support, which we will implement on the go. Let's put our blog-oriented stuff into another namespace for more readability. First, we need to define our business logic and the place to store blog entries. For now, we'll simply store blog entries in memory. In addition to storing blog entries, we'll also use another atom to generate unique sequenced IDs. The business logic knows nothing of the ring request or APIness. It just manipulates blog entries. Before we implement some actual handlers, we need to take care of handling the JSON format. As writing JSON parsers generators is a little too complex for this video, we'll use the standard Clojure data JSON library. Let's add it to the dependencies defined in project CLG file. Having business logic defined and JSON library connected, we can now provide ring handlers to respond to ring requests. First, we will define three helper functions, one to output the JSON response correctly, another to parse the JSON request body in case of post and put invocations, and finally a function to retrieve and parse the ID argument from the root parameters provided by the routing function. The parsing function will also use the Clojure keyword keys functions to make the JSON input data more Clojure friendly. We don't have to worry about de-keywordizing Clojure maps when generating JSON. The Clojure data JSON takes care of that automatically, converting all the keywords to strings. With the helper functions in place, we can finally define the actual handlers, each for every business logic function. Please observe how JSON structures convert almost seamlessly to Clojure maps and collections. After that, we can finally define our root handler with the previously defined routing mechanism. With the blog handlers ready, we can connect them to our main handler. As the blog handler is just another function, we can nest it inside of another routing call. Let's see our blog handlers in action. First, we'll start the Ring development server. Even though the JSON format is human readable, we'll use serial to invoke each endpoint more easily than from a browser. I will also use the JSON reformat command for more readability. It is only for the purposes of this video. You don't have to install or use it, although it may come in handy. First, let's create some blog entries. Please note that we are using the content type header to specify that we are providing JSON data in the request. Next, let's list our blog entries. We have received a JSON array in return. We can also access individual entries or update them and finally even remove them. We have implemented our first RESTful API with Clojure and tested it using serial. Please note that in real-life APIs, it might be feasible to abstract the handlers from the JSON format using the appropriate middleware, for example, Ring middleware format available on GitHub. Finally, in the next video, we will see how to handle errors in a way appropriate to the RESTful API. In this video, we will learn how to handle errors properly in our REST API. Returning error information is the key function of any API. We need to handle unexpected errors, wrongly formatted input, invalid parameters, authentication errors, and so on, in a clear and readable manner. With knowledge gathered before, it should be quite obvious what we need to do. That's right, create another middleware. As we don't support validation or authentication in our API, we'll simply capture Java exceptions and return the 500 internal server error response that contains the error details in its body. In real-life applications, other error situations should be mapped to the appropriate error codes as well. For example, 401 unauthorized for authentication errors, or 403 forbidden if somebody is lacking proper permissions. Let's create error handling middleware that returns error details in JSON format instead of HTML response as in the previous handler. We'll put it in the project1 blog namespace to limit the number of namespaces created, but of course it should be provided in a separate namespace or even library. The middleware simply captures the exception and returns its details as a Clojure map serialized to JSON. We will apply this middleware only to blog entry routes, as other handlers operate on HTML. Now we can test our error handling middleware. Let's start the Ring development server. And let's create an error nodes request. We have put wrongly formatted JSON content in the request body, which has resulted in a parser exception. Our middleware has intercepted the exception and returned appropriate information. We could, of course, put more information there if such a need were to appear. We have enriched our API with sample error handling. Of course, in an actual application, we would have to handle many different scenarios like authentication or validation, but now we know in which direction we can go with that. That concludes videos regarding building RESTful APIs. In the next section, we'll learn how to connect our Clojure web application to external persistence, such as SQL or NoSQL database. In this section, we'll learn how to connect to external persistence from Clojure web applications. We will first connect to PostgreSQL and add the connection management middleware. Then, we will configure the connection to access the database, create, retrieve, update, and delete data from a table. After that, we will also apply a popular Clojure SQL framework, Korma, to simplify our data operations and to use connection pooling. And finally, we will connect to a NoSQL database, MongoDB, and also learn how to manipulate the data. In the previous section, we have implemented a simple blog API. The blog entries themselves were simply stored in a Java virtual machine's memory. Such an approach has, of course, very significant drawbacks, like losing our blog entries upon JVM restart, and the fact that it cannot be applied in a production application. We need to connect to some kind of persistence engine, most likely a database. Fortunately, Clojure has a number of database connectivity libraries available, and we can just use one of them. Let's begin with connecting to one of the most popular open-source databases, PostgreSQL. We will use it to store blog entries from a previous section. We assume that the database is already installed on the local machine under the default port and has a user and schema named Clojure_blog created. For simplicity, we will use Clojure as the user's password. The first step to connect to a database from Clojure is to connect the appropriate libraries. We'll obviously need the PostgreSQL JDBC drivers, and we'll also use the Clojure wrapper for Java JDBC. Obviously, if you want to connect to a different database, for example MySQL, Oracle, or MS SQL, you would have to reference another driver. With the driver in place, we can create a middleware to manage our connection and transaction. We'll create a new namespace to keep it separate from the rest of the project. We will define the connection specification in PostgreSQL DB var, as business logic operations will access the database directly at this moment. With the connection configuration taken care of, we can now switch from the in-memory to the database for our blog entries. First, we need to create our database table. It will have the ID, title, and body columns. The ID will be serial to automatically generate values for us. Now we can alter the actual business logic functions to communicate with the SQL database. First, let's add the Clojure Java JDBC and Project 1 DB namespaces to the required list for the Project 1 blog namespace. Then, we can rewrite the business logic functions to use the database instead of Atom. We will not need the ID generator, as the database will provide it for us. As of version 0.3, Clojure Java JDBC does not provide a domain-specific language for SQL, so we will write our queries directly as we would in the database browser. One thing that we need to do now is to provide some structure by using only the selected keys from the input. Please observe that we use only Clojure data structures all the way. There is no need to transform them, just parse JSON and use a Clojure wrapper for JDBC. Having the business logic working on PostgreSQL now, we can finally launch the line development server. Let's test the API with PostgreSQL underneath. First, we will create an example entry. Let's see if it shows up on the entry list. To showcase that we are actually using the database, we can restart the Ring server. And the entry is still present. This concludes the first video of this section. We have connected to a PostgreSQL database and used it in our blog entries API. In the next video, we will see how to make our already simple queries even more simple with SQL ORM Clojure libraries. In this video, we will use a popular ORM framework to simplify our SQL database access. In the previous video, we have connected to a database and accessed it. Still, some things could be made a little better. We could have more polished access to database tables and use connection pooling. That's why we will connect the Korma library to our project. Korma provides two important features: DSL, that is domain-specific language, for generating SQL from Clojure, for simple code on our part, and database connection pooling with the C3PO library. Let's add the Korma dependency instead of Clojure Java JDBC to the project CLG file. Underneath, Korma also depends on the Clojure Java JDBC library, but we should reference it only from one place to avoid potential version mismatches. Now we can modify our connection handling namespace to use Korma-provided facilities, namely connection pooling. We'll use the same connection configuration and database, and we'll use the devdb macro from Korma to set up appropriate connection pools. Next, we will tell Korma to recognize our database table named entries with the deventity macro. Let's change the required namespace from Clojure Java JDBC to Korma core. Finally, we will rewrite our business logic to be more simpler with Korma. One thing that is different is that we don't specify the database connection. Korma takes the default one for us. The other is that Korma provides domain-specific language for SQL, so we can write our queries directly in Clojure. Naturally, fallback to plain old SQL still exists, as Korma is built on top of the Clojure Java JDBC package. Now we can start the Ring development server to see Korma in action. The result, of course, is the same as with a plain Clojure Java JDBC library, but our code is simpler and we use connection pooling now. This concludes the second video of this section. We have connected the Korma library to our project to access Korma connection pooling and domain-specific language for SQL, making things a little bit simpler. In the next video, we will connect to MongoDB. In this video, we will use the popular NoSQL database in our project. In the previous videos, we have connected to PostgreSQL and accessed one of the tables with our API. That approach, although useful, requires us to adhere to a fixed, from a Clojure point of view, database schema and to the SQL queries underneath. In Clojure, we are not limited to standard SQL databases, and we can use the provided libraries to many other solutions. In this video, we will connect to the MongoDB NoSQL database. First of all, we will need an appropriate library to connect to MongoDB. There are generally two options available if we use Clojure, either CongoMongo or Monger. Both of them use the official MongoDB Java driver underneath, but the JSON support seems to be a tad better in Monger, so we will use the latter. We will also add a dependency on Cheshire to enable JSON support for Mongo object ID types with Monger. We assume that MongoDB is running on a local machine in no authentication mode, which is sufficient for development, but not recommended for production use. We don't have to set up a database schema or configure tables. MongoDB will create collections and databases as needed, and every document can have different or even complex fields if there is such a need. We can now change our business logic to use MongoDB instead of Korma and PostgreSQL underneath. We don't need to pass a MongoDB connection either, because it is set globally. Moreover, we don't need to restrict on the attributes as well, although in a real-life API validation would be required. One difference is that with MongoDB, the default ID for a collection is stored in an _ID field, so we need to use it instead. As the ID in MongoDB is of type object ID, we need to convert it back from string. Conversion to JSON is done automatically with the Monger JSON namespace. As we have MongoDB connected, we can start the Ring development server to see it in action. The ID is different, but we can use it in the root handler anyway. One added benefit we get from MongoDB is that we are able to store comments inside of the blog entry document. Regardless of that, if it would scale well for thousands of comments, such flexibility is still useful in many cases. This concludes the database connectivity section. In this video, we have connected our API to the MongoDB database to utilize the flexible schema and simple connection pool management. In the next section, we'll use Clojure to access the API from a browser and to process its result. In this section, we will use Clojure not inside of the Java virtual machine, but directly in a web browser. Most web applications nowadays put at least some of the application or presentation logic inside of the browser. It is much faster and easier to manipulate browser contents using scripts running inside of it, instead of refreshing pages for every update. Moreover, in some approaches, most of the application's graphical user interface code is placed and run inside of the web browser. The downside is that JavaScript, which is used to script the browser, is not Clojure. Therefore, we need to write the application in at least 2 languages, which is already cumbersome. What if we want to build our application entirely in Clojure? Fortunately, thanks to Clojure, we can write our browser-side logic in Clojure and then compile it to JavaScript. The Clojure code shares syntax and language with Clojure code, but there are still differences and limitations. Therefore, Clojure code is placed in files with the CLJS extension and usually provided in a separate directory. Let's create a directory and first place the Clojure file in it. As you can see, it is a standard Clojure namespace. Here's something that is different. Just like we have access to Java virtual machines, mechanisms, and classes when running Clojure inside of JVM, in JavaScript, we have access to JavaScript objects and functions. Obviously, we are unable to access the facilities provided by JVM there. With the JSAlert function, we are simply invoking the JavaScript's alert function. In a browser, this will of course display a small modal message. Since we are already using Ring to build our project, we can add another plugin, which will compile our Clojure code into JavaScript. We need to configure the Clojure build plugin to tell it where the source codes are. Naturally, there are more Clojure build options than we have specified here. You can see the line Clojure build plugin homepage on GitHub for more complicated examples. Having the Clojure file in place, we can compile it to JavaScript. The first compilation always takes some time. For actual development, it is more feasible to run continuous compilation with line Clojure build auto. Even for large projects, it is still able to complete compilation in under 1 second. To run the generated JavaScript file, we will also need an HTML file to embed it within. Let's create such file. As you can see, there is not much here, only a reference to the JavaScript file actually. As we have generated a static JavaScript file, we can serve it with a wide range of HTTP servers, but since Ring server is at hand, we'll just use that. To run our compiled JavaScript, we'll simply open the created HTML file in the Firefox web browser. This concludes the first video of this section. We have created our first Clojure file, then we have used the Clojure line plugin to compile it, and finally we have run it inside of a web browser. In the next video, we will learn how to manipulate the browser's DOM tree from Clojure. In this video, we will learn how to use Clojure's access to JavaScript facilities to manipulate the browser's DOM tree. JavaScript, and in our case Clojure compiled to JavaScript, needs to be able to manipulate the browser's DOM tree for interaction with the user. In Clojure, there are a number of libraries that we can use, but to better showcase how we can access the browser's facilities from Clojure code, we will simply use JavaScript API directly. Of course, our operations will not be as elegant as when using one of the libraries, and the code might not work properly on other browsers. Still, for demonstration purposes, it should be more than enough. As we have our Clojure namespace in place, we can add more code to it. As you have probably noticed, the Clojure code is run without the need to reference it from the external configuration. This happens because all of the code is compiled with the Google Clojure compiler and made available to the browser in one JavaScript file in default mode. First, we'll remove the JSRlet function call. We will use DOM for interaction with the user now. Then, we'll reference the JS/document object. It is simply a document object provided in JavaScript. We can use it to create the object representing the DOM element and then access its methods by using a dot in front of the method name, just like when using Clojure inside of JVM. We can also access its properties by providing a dot and dash in front of the property name. We have created an anchor element and set the hyperlink attribute on it. We can also supply JavaScript methods and functions with a Clojure function to handle events, for example. And that's what we did to handle the click event on the anchor. In the last statement, we are attaching the created DOM element to the found element with the ID set to holder. It is of course not necessary. We have access to all the methods in the DOM, so we can approach this from lots of different angles. Let's update the JS HTML file to provide a container to which we can attach the elements created with ClojureScript. This is a plain document object model element. There is nothing Clojure specific to it. As you can see, it even contains some text content. Now we can recompile the ClojureScript file. Of course, in an actual development cycle, we could use the line ClojureScript build auto and run the Ring server in another terminal for a shorter recompilation time. Let's test our ClojureScript in the browser. As you can see, the ClojureScript that ran has updated the DOM by adding an anchor element. If we click on the link, we will observe a JavaScript IL with the element's outer HTML property. This concludes the second video in this section. We have learned how to access the JavaScript objects and how to interact with them at ClojureScript level. In the next video, we'll access the REST API created in previous sections and connect it to a web page using ClojureScript. In this video, we'll learn how to access the REST API with ClojureScript. In the previous video, we have accessed and manipulated DOM from ClojureScript. To have a complete range of tools for creating dynamic applications, we need means to communicate with the backend without refreshing the entire page. Of course, there are a number of frameworks, ClojureScript and JavaScript based, that make such communication much easier. Still, for showcasing purposes, we will simply use direct JavaScript objects and methods. Please note that the code we are about to implement will not work on older browsers like Internet Explorer 6 or 7, which provided different implementations for XML HTTP requests and even no native JSON parsing or generating support. First, let's prepare the HTML page for simplified blog content management. We will need an input for the entry title, a button to invoke the ClojureScript function, and a list to display the entries. As you can see, the button has a standard onClick attribute which references the add entry function in Project 1 Hello namespace. Just like in Java, we need to replace dashes with underscores when referencing Clojure-defined symbols from outside. This time, we will define actual ClojureScript functions in our namespace. We can remove the existing code as it is not needed now. We'll first define a function that takes a list of entries and applies them to an unordered list in the DOM tree. As JavaScript's DOM works on objects rather than immutable maps, we'll use the asset function to set the inner HTML property for the DOM element. Please note that we are iterating the provided data just like we would do with a Clojure collection. To retrieve the entry title, we convert the object Clojure using JS2Clojure function, and then we treat it as a standard Clojure map. After that, we need to fetch entries from the backend. We know that there is an endpoint under the /entries path, so we can just invoke it. We will set a simplified callback here that will ignore all the errors and just wait for the state of the XML HTTP request to change to false. Then, it will parse the JSON response from the backend and invoke the showEntries functions defined before with the result, a list of entries. The last function that we need is a function that we have referenced in the HTML code, addEntry. Please note that we use export here to uphold the function name during advanced compilation, which optimizes all identifiers. This function invokes the REST API as well, but this time we use the post method. We also set a header for the request and we provide a request body. To make a proper JSON string, we use the stringify function. This function takes a JavaScript object, which we can create by applying the Clojure to JavaScript function to a standard Clojure map. If we would like to convert the JavaScript object to a ClojureScript map, we would have to invoke the opposite function, JS2Clojure. Please note that in actual application, you might want to use EDN for simpler data mapping between Clojure and ClojureScript. To not complicate the screencast needlessly, we will stay with JSON. Finally, when the processing is finished, we invoke the loadEntries function to reload the entry list. And finally, we add the loadEntries invocation to the script. Normally, we would wait for the document to load, but for the sake of simplicity, we will just invoke the function directly. We can now compile the Clojure script. This time, we actually need the Ring server. Other than serving HTML and compile JavaScript, it will provide a REST API that we'll use. We can now add some entries and refresh the page to see if they work. If we open the developer toolbar, we will actually see some XML HTTP requests. We can even fall back to the standard CURL invocation of the API to see the list of entries added in the browser. This concludes the ClojureScript section. In this video, we have connected our REST API to ClojureScript for user interaction. In the next and final section, we'll see some popular libraries for Clojure web applications in action. In the final section of the screencast, we will familiarize ourselves with some popular Clojure web libraries. In previous section, we tended to implement things ourselves to get a better understanding of how everything works underneath. Of course, once we possess that knowledge, it is more important to deliver working solutions fast and in good condition rather than write everything from scratch. Naturally, there are a number of libraries aiding the construction of Clojure web applications. We will only cover a few of them in this section. First, we'll replace our custom routing mechanism with Compojure. Then, our simple HTML generation tool will be replaced by Hiccup. Next, we will apply Enlive for HTML templating. And finally, we will rework our REST API to use a Liberator. Let's start with Compojure. Naturally, we first need to add it to our project CLG file. Now, we can update the routes. First, we need to add a requirement for Compojure core in our namespace. Next, we can update our routing handler to use Compojure instead of custom routing mechanism. we have used some of the macros provided by Compojure. DevRoots creates a routing handler from the provided roots and binds it to a designated symbol in the current namespace. Just as in our routing mechanism, the first non-nil result is returned. The get and any macros define a handler that will execute its body only when the request matches the root definition, method type, and request path. Compojure provides utility macros for all HTTP verbs. Since we are using macros now, we can actually provide the function body and destructure the handler arguments of a request instead of just passing a function reference. If we have our handlers structured properly, we can use this to simplify our code a little bit. In our case, we'll just take the request map as it is and apply it to existing handlers. One exception is the form handler, which we will provide with the login argument. Previously taken explicitly from the request parameters, this will now be provided by Compojure. Please observe that our middleware and other handlers can stay as they are since they are using common ring conventions. So the blog REST API can still use our routing mechanism. One thing that we can do easily to group our REST API is to set it in a Compojure context, directing only the request matching /entries path there. The context macro takes a path, a list of arguments to be extracted from it, and a list of routes to be processed. Since we have the prefix provided in the parent root in the Project 1 core route handler, we can simplify our REST API even when not using Compojure for routing there. To make it work properly with the Compojure context, we also need to use the path info element of the request map instead of URI. Let's start a Ring server to see if everything is working as expected. The resources are served correctly and we can access the handlers as we did before. The parameter login has been passed with the aid from Compojure, and we can still use the REST API to manage blog entries through ClojureScript, for example. This concludes the first video of this section. We have connected Compojure to our project for easier routing, but we can still use other routing techniques and existing middleware if we need to. In the next video, we will learn how to generate HTML code with Hiccup. In this video, we will replace our custom HTML generation mechanism with the popular Clojure library, Hiccup. The problem of generating HTML code is as old as web applications themselves. We have approached it in the earlier sections and built a simple mechanism. Obviously, we weren't the first ones to encounter the problem, so we can use the Hiccup library to generate HTML instead. The first thing we need to do is add a Hiccup dependency to our project. Next, we should replace the reference for our HTML generation mechanism with the Hiccup namespace. As Hiccup is a well-rounded library, it provides several namespaces with different utility. Among these, the most important is Hiccup Core, which provides the HTML generation macro. But we will just use the Hiccup page HTML5 macro for an HTML5 declaration in our template, and Hiccup util escape HTML to make our HTML output a little more secure. Fortunately, the format used by our HTML generation mechanism operates on the same principle as Hiccup, so we only need to alter our layout function a little bit. Something we can use with Hiccup is tag attributes generated if the first element of the tag content is a map. For example, we can set the background color to dark gray with a white font. We can also use Hiccup util escape HTML to sanitize the output variables. Let's see Hiccup in action now. The form is static HTML. But, as we can see, the handler page gets correctly displayed with special HTML chars in the input, such as less than or greater than. If we peek at the source code, we will see the HTML special characters escaped properly. This concludes the second video in this section. We have learned how to connect and use the Hiccup library to generate HTML in the right way. In the next video, we'll use HTML templates with the Enlive library. In this video, we will introduce templating with the Enlive library. In the previous video, we have generated HTML code direct from Clojure using Hiccup. However, sometimes, not all people in the project have the time to learn Clojure, and some maybe use tools aiding them in HTML development, or are strictly web designers working their magic only in HTML and CSS. In such scenarios, it might be easier to have the template in plain HTML and just update its dynamic parts at the Clojure level. To achieve that in Clojure web applications, we can use the Enlive library. Enlive works by transforming HTML files with operations working on selected nodes, somewhat similar to what we can do with jQuery selectors on the client side. The operations can, for example, set node contents, add style and class names, and so on. Naturally, the first thing that we need to do is to add Enlive as our dependency to our project CLG file. Then, let's create HTML templates for our handler and general layout template. This time, the background color for the page will be dark blue. In HTML template, there is no Clojure-specific code, just some IDs if we need to distinguish parts of the document. Please note that templates are not in the public packet, so we will access them only Clojure side, not through a browser directly. Now, we can apply Enlive in our Ring form handler. We will only update the form handler, leaving the updation of session and cookie handlers using Hiccup as an exercise for the viewer. With Enlive's dev template macro, we are actually compiling the HTML file referenced in the first argument as a function rendering template. The function will take arguments and then apply the provided operations to elements matched by a selector. The layout template takes the contents and puts it inside of a body tag in the HTML template as a raw HTML code. The form handler template updates the contents of some pre-tags with designated IDs. The content function, in contrast to the HTML content, escapes its arguments. Of course, we need to update the form handler to use the new template. We need to apply stir, just like in the layout template, to transfer the Enlive output to HTML code. Let's start the Ring server and see our Enlive templates in action. You will also input special HTML characters to see if the output is escaped. As you can see, we have rendered the pages using Enlive templates. This concludes this video on using Enlive. We have connected the Enlive library to our project and used it to move our template from the Clojure code directly to HTML. In the next video, we will learn how to provide the REST API properly using Liberator. In this video, we will rework our REST API to use Liberator. In previous section, we have built and used REST APIs. As REST APIs should follow some well-known conventions and should be generally resource-oriented, it is much easier to use existing mechanisms, such as Liberator, rather than implement everything from scratch. Of course, Liberator is also Ring compliant, so we will be able to keep the other parts of our application intact. Naturally, the first thing that we need to do is add Liberator as a dependency to our project CLG file. With Liberator in place, we can rework our API to use it. We will also need Compojure here for ID resolution and routing. As Liberator will perform content negotiation for us, we won't be using the JSON response function anymore. With Liberator, we will actually define two resources. The first one for the list of blog entries, and the other one to support individual entries. The post handler responds to post requests, while handle OK responds to GET. As you can see, we don't generate JSON anymore, but we still need to parse it, unless of course it has been done before by an appropriate middleware. We won't be needing JSON error handler as well, as Liberator will take care of it for us. The other resource will support individual entries. This time, we'll support the get, put, and delete HTTP verbs. To prevent the use of put on the non-existing entries, we will set the can put to missing flag to false. Finally, we can reorganize the block handler to use Liberator resources. We still benefit from context mechanisms in Compojure. Let's start the Ring server. Now, we can test our Liberator-based API with ClojureScript. Everything is working as expected. We can also see how the put operation behaves now. Slightly different, but closer to REST API conventions, so it's an improvement. Other operations will be performed in a similar way. This concludes the final video of this section. We have connected the Liberator library and rewritten our API to be even more REST compliant. Thank you for watching. I hope you've enjoyed this series of screencasts.